Chapter 3 of the Recurrent Neural Networks course. In this chapter, we introduce the fundamental techniques of recurrent neural networks. This chapter includes the fundamental technical material on recurrent neural networks. It casts the supervised learning task in the principled form of adaptive non-convex optimization under dynamic network constraints and leads to the generalized form of the backpropagation through time. This holistic treatment brings systemic depth as well as ease to the process of adaptive learning for general, that is, gated and ungated, recurrent neural networks. This is the outline of this chapter, from reviewing the simple recurrent neural networks to introducing the basic recurrent neural networks. Let us start with reviewing the simple recurrent neural networks. This figure shows the architecture of the simple recurrent neural networks. You could use this figure as a reference when we go into the details of the equations of the network. As we have seen in the previous chapter, the simple recurrent neural network, SRNN, can be viewed as a single-layer recurrent neural network where the activation is delayed and fed back synchronously with the external input. The result of the activation function, denoted by H_t, is shown in equation 3.1, as we have seen many times before, where t is the discrete, real or fictitious, time index. S_t is the n-dimensional external input vector. H_t is the n-dimensional output activation via the nonlinear function sigma_t. Sigma_t is a general, possibly time-varying, nonlinear function. The n times n matrix U, the n times m matrix W, and the n times 1 vector bias B are training parameters. In equation 3.1, recurrency, or feedback, is expressed by delaying the output activation function H_t, transforming it by the matrix U, and feeding it through the nonlinear function sigma_t. Remark 3.1 from a system and signal processing viewpoints, the model in EQ. 3.1, without the nonlinearity, sigma t, represents a linear filtering that can be expressed in the Z-transform as follows. In general, the Z-transform represents a high-pass filtering, and thus all high-frequency input components, including noise, will pass through to the output. We can rewrite this SRNN architecture as equations 3.2 and 3.3, where we explicitly identify the internal state vector x_t. Equation 3.2 captures the dynamic and stability behavior. Equation 3.3 is a static nonlinear mapping of the state to the activation state H_t. The stability properties of the network are determined by the matrix UH'_-1, where UH'_-1 represents the diagonal matrix of the derivative of the vector H_t-1 at the state x_t-1 value. Unstability of SRNN. Since the matrix U is typically initialized to be randomly small and is adaptively changing over the training iterations, the UH_t-1 may exhibit or lead to unstable behavior of the dynamic network during the training phase. If at the end of training, UH_t-1 is an unstable matrix, the system may become unstable, which may lead to x_t growing without bound. Even the activation H_t is bounded when using a compressive nonlinearity for sigma_t, x_t may still grow without bound. Of course, Lyapunov theory and Lyapunov functions would constitute a definitive approach to confirming the stability of the overall nonlinear network during or after training. As shown in the figure on page 6, the SRNN has an output layer which is defined in equation 3.4 and the output probability is defined in equation 3.5 where Z_t is an r-dimensional output vector and P_t is the output probability vector. As shown in the figure, the output probability is usually obtained by applying the softmax function. We have seen equations 3.2 to 3.5 in the previous chapter, which is a standard definition of a simple recurrent neural network. In this SRNN, we can observe that first, state x_t represents the information of the input sequence up to, and including the instant t. Second, there is a single pathway from the input S_t to the output Z_t. For training this architecture, stochastic gradient descent is the most common approach. Why we commonly use the stochastic gradient descent to train the network? First, it has been found to do a good job in practice in training neural networks in general. Second, the ingenuity efforts have been focusing on innovative designs of network architectures while keeping the training methods within the families of the stochastic gradient descent. Third, while the stochastic gradient descent requires sufficiently large amounts of training data for high accuracy performance, this is no longer a problem due to the abundance of data for many applications. Fourth, The advent of high-speed and parallel computing, think of GPUs and cloud computing, algorithmic executions can be achieved in reasonable times. While many deep learning frameworks, for example, TensorFlow and Keras, PyTorch, etc., hide the training methods under the hood, it is important to understand the details for technical understanding of the methods as, more importantly, to perhaps have to extend or innovate such methods in the future. Let us walk through the process of parameter update using backpropagation through time. The backpropagation through time is simply a recursive computation of the stochastic gradient descent using the derivative chain rule in basic calculus. We first define the loss function as an expectation of the finite horizon loss sequence as shown in equation 3.6 where n prime is n+1. We now compute the gradient of the loss function with respect to each parameter in the RNN model, which can be expressed as equation 3.7, where delta theta is the simple approximation of the time derivative. Eta is the learning rate. For parameters that are not in the neural network model are often called hyperparameters. Let us derive the detailed expressions for the gradient for each parameter in the simple recurrent neural network model. For the loss function, we will ignore the factor 1 over n prime as we can integrate that part into the learning rate eta. First, we define the column vector e_t as the derivative of the loss function to the output parameters e_t, as shown in equation 3.8. Then, we get the partial derivative of the loss function to the weight matrix V as shown in equation 3.9. This derivation is based on the chain rule in calculus. Note that based on equation 3.4, we can easily obtain the derivative of z_t to V as h_t. In the matrix format, we denote the final result as the summation over t, e_t times the transpose of h_t. Similarly, the derivative of the loss function to the bias parameter c is shown in equation 3.10. Note that the derivative of z_t to c is a constant, or specifically, is 1. To compute the partial derivative of the loss function to the internal state x_t, we let lambda_t denote the derivative as shown in equation 3.11. In some references, lambda_t is referred to as the delta variable in the backpropagation through time. Lambda_t can be expressed based on variation principles as a backward-in-time dynamic equation in equation 3.12. Recall that sigma is the activation function defined in equation 3.3. Equation 3.12 can be derived from the fact that the variable x_t forwardly connects to the output at time t and the next time t+1. We will explain the variation principles later in the next section in equation 3.44. For the partial derivative of the loss to the parameter matrix U, we can get equation 3.13 using the chain rule. The partial derivative of the loss to the parameter matrix W and vector B can be obtained similarly, which are shown in equations 3.14 and 3.15, respectively. The gradients associated with the RNN dynamic equations using the backpropagation through time are sketched in the figure shown in this slide, where V is set to the identity matrix and C is set to 0 such that they are omitted in the figure. When training the recurrent neural network using the stochastic gradient descent, we may encounter the vanishing gradient or the exploding gradient problem. As a consequence, recurrent neural networks may be difficult to train by the stochastic gradient descent in practice.